but the test is whether you can actually hear something. Can you? Okay. All right. First, thanks for the invitation, and for the organizers, Filippo in particular, for a beautifully run meeting. I must say it's a tremendous pleasure to be in Florence every time, and then to top that off, to climb up this hill and come here. It's really great. Okay, now to the subject. Let's see. This worked just a moment ago. Yeah. Okay, I'm going to be talking about vertex models, and this is going to be a very simple talk. No fancy theories or complicated formulas. Might even be short talk, but we'll see. Okay, so in particular, zero flux vertex models. By that I mean on the square lattice that there's a same number of incoming and outgoing arrows, so no spin variables. You just set these arrows according to that rule, and then the model is what you get when you do that globally. So the best known example is, of course, the 6 vertex model, which these are the 2 vertex configurations allowed with the multiplicities. And I think everybody has seen that many times over. And a whole lot is known about that. And there are very interesting things happening there, including the limit shape phenomenon. Now, in this picture, there are also 2 of its higher relatives. The 15 vertex rule, which you get by taking all of these. You take these extra allowed configurations, and the dotted lines means that you now allow actually unoriented edges as well. You still keep this zero flux rule, but you allow unoriented vertices. I mean, unoriented edges. And furthermore, if you look at this, you notice that there are some rotations missing from here, exactly 4 orientations missing. So 18 vertex rule, you remove the anisotropy from this rule, and you actually take these 4 missing vertex configurations, and you get 19 total. And these are the 2 that I'm going to be talking about here today. Just a caveat, 8 vertex model is also a close relative, but because it has sources and sinks, so it doesn't belong to this family, so forget about that. It doesn't help you in this context. About 15 and 18 vertex models, here are some references to the literature that has appeared over the years, including some of the fairly recent ones. Some of these have considered the model on a bounded domain, but mostly not, or well, Thorough domains are certainly bounded, finite, but not bounded. I want to consider this on the simplest bounded domain, a square, just to see how much the behavior starts diverging from that, what is known for 6 vertex model, to be able to compare to that, and also for alternating sane matrices and to dimer models, which have been studied on square or diamond domains. And the questions that I want to sort of, in a general way, the questions that I would like to get some answers is that ice you can view as a model of fully packed loops, directed loops, and the entropy in that model arises from the only thing that you can do there to perturb the configurations, which is reversal of these unidirectional loops. And among those, short loops are the ones that carry most entropy. And if you know which ones you can act on them, then you can actually localize where the entropy is generated in the configurations, meaning how many relatives they have when you do this kind of a perturbation. Now, 15 and 18 vertex models are more complicated because the loops are diluted because of these unoriented edges. And turns out that to generate all the configurations for these models, you need multiple actions that you will see shortly. And then the question is that on a finite domain, like a square, with some reasonable boundary condition, how do these actions work there in different parts of it? Are there maybe frozen parts where the action can't do anything, and then tempered parts where things happen? And in particular, if you can find out something interesting about this, then could you then allude something about possibly limit shapes in these models as well, these higher vertex models? Okay. First, some static bits. So the height function is probably, most of you are familiar with that. But just to review, you go to the dual lattice or the square lattice, and you define this height and integer value function there in the following way. You choose a reference point where the height is 0, and then when you move away from that, if you cross an arrow that's pointing to the left, the height goes up by 1. If there's no arrow, the height doesn't change, and if it points to the right, then it decreases by 1. And by this zero flux thing on a simply connected domain, you get a uniquely defined function from this. That's your height surface, and you can think it as a continuous surface, as a Lipschitz surface, but what is actually maybe more useful to think about it as a stepped surface, so that you have this 1 by 1 ceiling pieces sitting centered at every dual lattice point, and that covers your configuration. Okay, on this then you can define a partial order the way described here, that if you let these to be solids under this stepped surface, then if you have containment like this, then you define that C is superior to C prime. So that's a partial order on these configurations. This is a useful thing to know. And another useful thing to know is that these have the structure of a distributive lattice. And what does that mean? Distributive lattice is a triple like this, V and wedge, such that for all X and Y, this thing holds. And also the other version of this formula where you have the V's and the wedges interchanged all over. And the important property here that these distributive lattices have is that they always have a maximal and minimal elements. And now this is a general combinatorial structure, and it becomes useful through this simple observation that when we are in this setup that I described on a square, and we have this partial order defined, then the configuration sets are actually forming a distributed lattice. So in particular, then there is the maximal element, minimal element, and this in the proofs in the results that are coming. These two things are important little bits in there to complete them. Okay. So then, no, the other arrow. Now I want to do a dynamical version of this these vertex models. So we know that all unidirectional loops or infinite loops, if we are on an infinite domain, they can be reversed. And then additionally, in the context of this model, there should also be some operation that converts directed paths into undirected paths. And to have an efficient algorithm to do something like this, we should consider the minimal loops where we can do this sort of things. And this leads to these legal actions, which are with various names, local moves or flips or so on. That I'm sure many of you have seen in the context of, for instance, dominoes. In the domino context, the flip is when you have two domino pieces next to each other, the long sides next to each other, and you flip that by 90 degrees. That's a local move in the domino context. So here's the local move for ICE or 6-vertex model is this alone. This is enough to generate all of the 6-vertex configurations. These in here, the numbers around are the heights defined the way it was on the previous slide. And so you notice that the height in the center obviously changes when you have these orientations reversed. Now, when you go to the 15-vertex rule, then you need to add something more because the unoriented edges are allowed, and you need to. This is the action that you need to add there. This together with the same thing rotated by pi, 180 degrees. Then these two actions together, they generate all the configurations. You're given one configuration from that model, either 6 or 15, and then with these actions, you can generate all of the others. Things get a whole lot more complicated when you go to the 19-vertex rule. And this is the minimal set that you can get away with. So you notice that this ICE action is there. It has to be there because ICE is embedded inside this about 15 and 19-vertex rule. But then you need also this action, which was on the previous slide. But in fact, now because the isotropy is removed, is imposed on the 19-vertex rule, you have all the rotations of this, not just the one rotation by 180 degrees on the previous slide. And then additionally, we need this move and this move, and then this creation move in here, indicated by these arrows in here. These fractions in here are probabilities, and now I parameterize this in here with B and Q because I want to play with those a little bit later on. But this is the minimal set for the 19-vertex rule that that you can generate everything. And yeah. Sorry, it probably is all 1/2 what?
What is the other option besides the 1/2? It needs to normalize to 1.
Well, I mean, you might want to take different intensities in how you create or how you annihilate in here.
Okay, this I understand, but on the right-hand side, right now you have this is the only change you creation annihilation, but still the what probability.
Sorry, I don't understand the question.
So if I probability plus 1/2 should be 1, right? For this probability pool.
No, these are both between 0 and 1. You can choose these any way you want. And I mean, to begin with, you know, just assign any values to them. I'll talk about this later, what happens when you do different values with them. This 1/2 is just here. Well, basically, I'm heading a little bit ahead of the story, but to have detailed balance, you need to have 1/2. So that's basically the best situation where we would like to be, but it's also of interest to look outside that.
Okay, we can discuss later. I still don't understand.
Yeah. I'll say a little bit about weights in a moment. Okay, so this set it's easy to see that it doesn't generate, there are 2 sets now, new sets, the 15 vertex model and the 19 vertex model cases. It's easy to see that they don't generate any illegal configurations. What's a little bit trickier to show that you actually capture the entire legal configuration set. And one useful way of thinking about this is actually to think of these actions as sort of deposition of sublimation of little pieces, either unit cubes or 1 by 1 by 2 upward standing pieces, which you drop on the stepped surface, or you remove it from it. And with those things, you can build higher or lower configurations. And for instance, to show the irreducibility of the set of configurations, you want to reach either the maximal configuration or the minimal configurations, which are guaranteed to exist because it's a distributive lattice that you are acting on. This kind of a geometric thing helps you to figure out that in fact, these are the sets that you can get away and you don't need to have extra actions on top of this. Okay, and once you're convinced of that, then you know that you can actually do a Markov chain with this. And I stated here, this part is for 19 vertex rule, but the same thing holds for 15 vertex rule and obviously for 6 vertex rule as well. So with these stated elementary actions, you can get the irreducibility, and then you get a periodicity when you have these parameters like this, and then you get the ergodicity of the Markov chain. And so this is like, this theorem covers all these 3 models because I've specified what the flip actions are for each of them. Okay. So then this is sort of a practical slide. What you do when you implement this is that you either in the 6-vertex model you have your symbols are what you get when you do the coding around each lattice unit square. So either you have 16 or 81 symbols in your alphabet, depending on whether you allow the unoriented edges. And what you do is that you take an array of those, and inside that you have a smaller square, and that square is the one where you actually end up putting the boundary condition, which I'll talk next. And you then update that according to some scheme. You can do updates on distinct unit squares independently, which is of course very valuable property. Or you can do it with some exponential clock or whatever scheme. Now, coming back to this question about the weights, the static weights, that the only ones that will definitely work are the uniform weights, because you basically, when you do this, for instance, in the 6-vertex model, if you do the reversal of a unidirectional loop, you interchange A and C type vertex configurations at the corners. So they got to have the same weights in order for you not to violate it immediately. On the other hand, there's some gain. This particular thing allows, I mean, it's easy to show that this is actually a so-called monotone chain, which means that it's compatible with the partial order that was defined. And then this technique, which some of you might have seen, coupling from the past, for exact simulation is available. So, yeah. With the same weight, all of them with the same weight. Yeah. I'm not familiar with those models, so I can't answer that. I just view this as a sort of a combinatorial structure and do what is doable with this machinery. Maybe we can discuss that afterwards. Okay, so then to get into actual computations, here's the array where you have these unit squares, which are the actual variables in this computation. They are sitting in here. And if you specify, for instance, the arrows like this, that on this boundary, all these arrows are pointing in, these are pointing out, these are pointing in, these are pointing out. What happens is that then these are forced then to point in. And these are forced to point out, point in, point out. And then you recognize that this is actually the domain wall boundary condition for a 6-vertex model. So in terms of height, this means that if you put this kind of a boundary condition here, and here it's height-wise, it's flat. It's flat. So the surface is actually a ridged roof. The height surface that you are using here. And this domain, this is actual domain where you consider your model. This is where you get here the domain wall boundary condition, if that's what you want to do. Okay. So a couple of observations regarding to this. with 15 vertex model, there's no point of putting the domain wall boundary condition there because the model reduces immediately to 6 vertex model. So in order to do anything interesting with 16 vertex model, this is what this first proposition says, is that you better generalize it outside domain wall boundary condition. And this is just something to help a little bit to see what's happening in a moment when we do a more general condition, that if you do boundary condition, if we do unoriented edges, then the number of them inside the domain remains constant, and they sort of behave like you would think them as Brownian bridges, which are endpoints on opposite sides of the domain, and then they wiggle in between. You will see in a moment. This is not at all true for 19 vertex configurations. That's a very different thing, also exhibited later on. So what might we then do for 15 vertex model? Let's consider that first to get something interesting happening. Well, the simplest thing, this is the ridge roof cross section, and this is not going to bring us anything new. But if we shave the top like this, which means that we put two unoriented staircases at the top of this in here, then that should be already something which you can't do with 6 vertex model, but which might be of some interest in 15 vertex context. And this is a bit more complicated one. An illustration of that will follow. But let's first see what happens with this K-type thing. So here's this is the diamond, and the ridge of the roof is horizontal in the middle in here. So the actual domain is now, this is tilted 45 degrees. The actual domain is in here. And what you see in this part in here is at the equilibrium where the action 2 takes place. This is where action 2 takes place. Sorry, action 1 takes place. And here's just a reminder of you. 2 is the one where you had this L-shaped thing which flips over like this, and the other side is unoriented edges. And 1 is the action which flips fully oriented one loops. And just summing these up is this. These are density plots from these distributions at equilibrium. So the darker it is, and the darkest is at the center, is where most activity takes place. And then when you approach the edge, then gradually the action becomes more and more difficult. And then at some point, you can't anymore act on the configuration. And that's where you enter the frozen part of the square domain. If you actually look at a little bit differently, well, this in here is in 3D plot. It's like this. These are the two distributions merged together and shown together. You can't distinguish them. And this is just for the sake of seeing that there are actually two distributions. When you weight this part tenfold compared to this one, then you can see where it is in there. So that's it's this thing in here corresponds to this part in here, where the action 2 takes place. So if you like, it's kind of like a food chain that when the unoriented edges are at the top in the beginning, they start going out, when there's this relaxation period, and then this action 2 converts them in such a form that the action 1 can start working on them. So that's how they sort of work in unison. Now, if you do a T-type boundary, that means here that in the beginning of this simulation, there was on the top at the ridge is still this horizontal thing in here, which is not shown, but here there were 2 blank unoriented ribbons across this domain, and then another blank ribbon in here and another in here. And then you start running it, and eventually you will get to equilibrium. And for this action 2, it looks like this. And for action 1, it looks like this. And these together, it's this thing. No, the ribbons are individual paths of unoriented. It's a sequence of unoriented edges that goes from one side to the other one. It doesn't have any width. Yeah. Originally, there are 2 of them next to each other. And then because of the dynamics, they start sort of sliding down the ridge roof, one to the other side and the other one to the other side. And then this blob, which is the same as the blob that you see in 6-vertex model, that starts forming in the center there. This last picture in here is actually where the actual unoriented ribbons are at the end of this equilibrium run. So this is a snapshot. These are cumulative plots, these 3 in here, like said in here somewhere. And this is a snapshot of one instant at the end of the run. And I mean, obviously, these are just experimental things in here that I'm showing you what this algorithm gives you. But I think, at least to me, this looks like some things could be proved in this context. This just should be something that can be attacked, for instance, with the tangent method of Colombo and Sportiello to figure out what exactly is this curve in here that you got, how much it differs from the square. I mean from the round shape. Okay, I have to rush now a little bit to say something about 19-vertex model as well. So this is the setup with the parameters B and Q, and notice at the bottom in here, if Q is 0, that means that no oriented, fully oriented unidirectional loop is ever going to be killed. Q is the rate at which you kill it, so the probability. So if the probability is 0, they will always remain there. So the bottom is just ICE model, independent of B, because ICE model is fully packed with loops. There is nothing to be born in there. There's no sites that could give birth to oriented loops. And a couple of other things. I gave a funny name to this corner point in here, anti-ice, for the following reason. We want to look at that because what's happening in here? Here, the birth rate is 0 and Q is maximal. So if there ever appears a, let's say we take a domain wall boundary condition or something like that, think in terms of domain wall boundary condition. If there ever appears a oriented unidirectional one cycle, it's immediately removed from there. So there's no ice dynamics left in here. Remember those reversals of one oriented one cycles were the ones that gave you all of ice. If you remove that dynamics completely, then you're at that point. So what actually happens there might be of some interest to look at. And then we will look at this diagonal as well in here. And this is what these dots in here just indicate where I looked at this model. So, I mean, I'm not doing these simulations for work. I only do to try to get some sort of insight what might be going on in these models. You could do this in a much more comprehensive way, obviously. But before I show you what is actually, what you get to see there, is that one useful thing to notice is that the arrow density, even with this domain wall boundary condition, can fluctuate anywhere between 1.5 over the runs over the domain. So for this model, for 90 vertex model, we stick to this boundary condition because that's already gives you a rather rich spectrum of different kind of behavior there. So all the subsequent samples that you will see in the next slide are with the domain wall boundary condition at equilibrium, and parameters are varied a little bit. If the parameters B and Q are equal, if you're on the main diagonal, then you have detailed balance. Otherwise, you are off, except at the bottom, the ice case is there, the parameters don't matter. So that's also within detailed balance. So here's the first thing. If you just look at configurations, this is ice at equilibrium. You can see the limit shape thing forming there. A bit rough, but it's not such a huge thing. It's only 100 sites on the side. This is the hot ice, the one corner, and the alphabet is now bigger, so that's why the picture looks a little bit different, but you can start suspecting that the limit shape is still there. But what is actually, I think, at least this is much more illuminating, is to look at these supports of these distributions of the different actions. What do we have in here? Let's start from the bottom row in here. This is ice. This is ice model, the one that you've seen many times over. Underneath here, I list what the action is, and above it is supposed to be the distribution of that action during some period at the equilibrium. Well, in the ice, the only action that you have is the action number 1, which was the one that where you flip the unidirectional one cycles, clockwise or counterclockwise, you change the direction. And this is what you see at the equilibrium. The lighter the image is, the more there's activity. And then when you get further out here, it gets dimmer and dimmer, and eventually it drops to 0, the lightness, which means that you hit the frozen part of the domain. Here, this is the actual square where you have the domain wall boundary condition. So the diamond has been now stripped away just to fit the things better in the slide. So this shows the actual domain here. And you have the domain wall boundary condition on it everywhere here. And as it's now known, this curve actually here, which bounds this support, or is its boundary? It's the one that comes from one weight ASM, or the delta equals to 1/2 for the ice model. Okay, so this is ice. Now, if we go to this middle row, that's a diagonal on this in here. So we're on the main diagonal here. And you see that all the actions are there, and this is where they are happening. And the notable thing about this is that this action number 2, which is, I know there are a lot of these things that I'm talking about here. This is the action where you have 2 arrows like this, and you flip them over like this, or in a different orientation, but that's the sort of a corner thing. This has the largest support and the sharpest edges. And it looks very much like this is actually going to define some sort of a curve in the scaling limit. These others are just supporting actors in there, which are doing their part of entropy generation, but not close to the border. So they influence the distribution inside the domain in various ways. But as you can see, their boundary is sort of tapering off. So it's this is actually pretty steep in here. If you look at the sections, I have those also in another plot. If you look at the sections of these distributions, they drop in a very steep way. Okay, so then what about the top? The top is the anti-ice that I advertised a moment ago. Okay. Now, B was 0 there, so there were no births of these oriented cycles. So that's why this is blank. But you can see that still you have this thing in here, meaning that this too seems to be defining the some sort of a curve that tells you where the action stops and outside which the configuration is frozen, which is kind of surprising if you think about that. You take ice model, then you generalize that model into 19 vertex model, and then specifically you take away the mechanism from that new model that was responsible for this behavior of the ice model. You take that completely away, but you still have behavior in terms of this, which at least to me, it looks like there should be a spatial phase transition, and it's defined by this action. And these 3 others are then supporting. They are generating entropy to the system, but not close to the boundary. Okay, I'm almost out of time, so let me just. Okay, though, what I should say about here is that these have been scaled for contrast. So the actual intensities are roughly like this. And I don't have time to go to that, explaining exactly how the magnitudes are, but have to give that away. So here's just a snapshot of at the end of equilibrium, at equilibrium of the ice configuration and then anti-ice configuration. It's a little bit more squarish, this outside boundary, if you imagine it there, but there definitely seems to be a sort of a tempered and frozen domains there. Okay, now one final thing that I want to say is that because this thing that action number 3 was the most intense in all of these simulations, it was kind of interesting to see what happens if we fiddle with that, meaning that you introduce asymmetry into this, which is the action number 3. Now, mathematicians, computer scientists do this, without much worry, but of course, physicist immediately says that you're breaking the detailed balance, which is a major sin. But nevertheless, if you do that, maybe at least you can take a look at what happens. And rather interesting things happen if you fiddle with this action. This is the anti-ice from the previous slide. The first square is removed because that was blank. There was nothing happening there. And now with different p-values, you get at the bottom p is 1/8, and at the top it's 7/8. You can see that there's a quite a drastic change in where these actions take place for this kind of model. Okay, I think I'm out of time. Thank you.
Thank you very much for this talk. Are there any questions? We have time now.
I mean, just to make sure, I mean, in your last slide, or previous to this one, I mean, you do indeed find this inner facet, right? I mean, so the interior, I mean, the domain in the middle, which is presumably sort of macroscopically completely flat.
You mean
this one, yeah.
This thing in the center.
Yeah, I mean that's presumably it's not perfectly. I mean, it's not perfectly ordered, but you have small errors. But otherwise, it will be on the macroscopic scale. It will be completely flat. Is that correct, or is that?
Oh, I think so. Yeah.
And I mean, this is sort of like I mean, of course, I mean, for the anti-ferromagnetic 6-vertex model. I mean, that's a very well-known phenomena. I just wondered whether can I think of this sort of as an extension of what people have seen in the 6-vertex model, or is it some completely new animal, or how does it compare? I mean,
I can't really say whether it's new thing or whether you could relate it to that.
I mean, does it have this sort of anti-ferromagnetic order of lines? I mean, sort of for 6-vertex model, you find sort of a line, and then sort of I mean, sort of anti-ferromagnetic. I mean, these are just lines, sort of, let's say a plus line and then a minus line and a plus line and a minus line. I mean, this is what you find for the in the anti-ferromagnetic domain of the 6-vertex model. I just wonder whether something similar happens over here, or maybe has a different structure.
Wish I could answer that. I don't know. It's well, at least I shouldn't claim that it's something completely new, because I just don't have argument for that.
Yes, sorry, maybe I missed something. I don't remember what was what is P. Here you are essentially playing with P, right?
P is this parameter.
Okay.
How much it differs? Before this, P was always 1/2. But now I introduced this asymmetry in this very last part.
Okay, thank you.
Yeah.
Are you still satisfying detailed balance, or are you actually changing, you know, I mean, are you still satisfying detail, you know, what you mean by P and 1 minus P? I mean, you're still satisfying detailed balance?
No, detailed balance is violated in here because now the chain is not, I mean, the Markov chain satisfies detailed balance when you have the jumps to both directions with equal probability.
But what are you simulating then if you don't satisfy detailed balance?
Well, there will be some, you know, whatever probability current left at the equilibrium.
Oh, I see.
So
okay.
it you know, requires some further study what is actually happening there, but it's not the same kind of equilibrium as what you have when you had the detailed balance.
So when P is not 1/2, you will not have a probabilistic stochastic, probabilistic cellular automaton anymore, I guess, right? It will be some other kind of transfer operator.
Well, I mean, it's probabilistic cellular automaton all the time, but what you don't have is detailed balance when you.
So you, in any case, you conserve probability from step to step. Or I mean, it's a really probability conserving transfer matrix. Or yeah, is it? Yeah. Okay, right. Okay, right. So what happens if you take just the limit P equal to 0 or P equal to 1?
Probably something weird. I haven't checked. I mean, this was already extreme enough for my taste to see something like this.
Well, I mean, one gets some insight where it goes, right? If you take it to the extreme.
Yeah,
okay. Yeah. Hey, are there other questions?
I mean, what I think is also interesting in, or sort of this bottom row is incomprehensible to me. I would be very glad to discuss with anybody who has any ideas what's going on in here. But in here, the thing that these seem to have a bit similar kind of support, these distributions. And this is the case that where you're actually going to the direction where directed paths are more and more convoluted and possibly lattice filling in this square lattice. So it's a little bit similar situation that when you do something like Schramm-Loebner evolution, and you put the parameter in such a way that you start seeing space filling things, then you are encountering certain new phenomenon there. I don't know if this is related to that.
Okay, then no other questions, then let's thank the speaker again.